So the plan for today is to just do a few more examples as to how we can actually solve AC circuits. We said if we have like a circuit that has AC sources, in particular if it has like sine waves, instead of analyzing it in time domain, we can take it to the frequency domain. So we have to like convert all the elements to the frequency domain. And as soon as we convert everything in like with their equivalent in frequency domain, then we can treat all the elements as like a resistance. And we have something very similar to Ohm's law. So we can basically use all the methods that we had before. KVL, KCL, mesh analysis, superposition, all those things, right? The only catch here was, as soon as I go from time domain to the frequency domain, I'm going to have to deal with a bunch of like complex numbers. The rest would be exactly the same. And what we're going to be doing today is that we're going to try to like use like those methods like KVL, KCL, mesh analysis, Thevenin and Norton to solve a circuit to see like it's exactly the same and nothing basically changes. Okay? So let me quickly remind you of like what we have. So solving AC circuits with sine wave. The first step is to draw the circuit in frequency domain. And to do that, we're going to have to convert all the sources that we have, which means like if I have like a sine wave as a source, I have to convert it to the phasor representation of it. And if I have like my elements, I have to like replace them by their equivalent, right? So convert sine waveforms to their phasor representation, which if you recall, we said a phasor representation only requires us to have the phase and the magnitude. And we said the main signal that we have is a cosine. So if I have x of t some xm cosine omega t plus theta, we know the phasor representation of this x of t is x with magnitude xm and the phase theta. And if x of t was represented in terms of a sine wave, all we have to do is to convert this sine wave to a cosine and write the phasor representation, which becomes x equals xm theta minus 90 degrees, right? And then we're going to have to convert all the elements. So if I have my time domain elements here, VI relationship in time domain and VI relationship in frequency domain, and we have like this impedance. So if I have a resistance with value R, I know the time domain relationship, Vt equals R times It. The phasor representation is V equals R times I, which we know V and I both are like phasor representation, which means they're complex numbers. And if I want to know, for example, the phase of this V, I know phase of V is phase of R plus phase of I, but R is a real number, so it does not have any phase. So it's 0 plus phase of I, which means V and I are in sync. Whatever phase I have for V, it's the phase for I. So they're basically in phase. So V and I are in phase. And this R over here represents our impedance. So we know if we have a resistance in time domain, the value of the impedance in frequency domain remains the same, and it would not change, right? If I have an inductor with value L, I know VI relationship is VT equals L DIT dt. The phasor representation would be V equals I omega L times I, which means to find phase of V, I have to have phase of I plus phase of I omega L, which is the same as phase of I. And we know the phase for I is pi over 2. Therefore, phase of V is pi over 2 plus phase of I, which means V leads I by pi over 2. So V leads I by pi over 2. And of course, the impedance would be I omega L. And as you can see, the impedance in general is a complex number as well. And this complex number is being controlled by the frequency of the circuit, right? It depends on this omega. And if I have a capacitor in time domain with value C, I know the IV relationship is IT equals C dVt dt. The phasor relationship is V equals 1 over I omega C times I. So to find phase of V is phase of I, phase of current, plus phase of 1 over I omega C. This second I is the complex number, right? So we know phase of 1 over I is the same as phase of negative I, right? Which is negative pi over 2, negative 90 degrees. So what it tells me is that V lags I by pi over 2, or I leads V by pi over 2. So V lags I by pi over 2. And we know if we have a capacitor with value C in time domain, the impedance is 1 over I omega C. But we said like it is easier for us to have this I on the top, so we wrote this as negative I over omega C. And as soon as we convert the circuit to the frequency version of the circuit, life is like easy. We can apply like whatever method that we had before. So the idea is that step 2, solve the circuit using your favored method in frequency domain. So for example, you can do KVL, KCL. You can do voltage or current divider. You can do mesh or node analysis. You can do Thevenin or Norton. You can do source transformation. Or you can do superposition. And this superposition is particularly very useful if the circuit has two different like frequencies or multiple like frequencies. If you guys remember, I told you guys like if you have a circuit that has like two sine waves, one is operating at like one frequency, the other one is operating at the other frequency, I cannot convert the circuit to the frequency domain, because to go from time domain to the frequency domain, I need to have one frequency, right? What I can do is that I can apply this superposition in time domain, right? And zero out basically all the sources but one. Now I have a circuit that's operating at exactly one frequency. Now I can take it to the frequency domain and solve it the way I want, and then convert it back to time. I can do this for all the sources I have. And I know the superposition actually holds true in time domain. So this superposition is particularly useful if you have like multiple frequencies. So this is particularly useful when we have multiple frequencies. And now we have the solution in frequency domain. We got to take it back to time domain, right? Given the frequency that we have, we can always go from frequency domain to the time domain because there is a unique relationship. So the last step is to convert the solution back to time domain. Right? Let me quickly tell you like how voltage divider and current divider works in frequency domain. But again, remember, it is exactly the same as before. There's nothing new. Just want to give you like a quick reminder. So reminder, if I have a voltage divider with value V, Z1 and Z2, if I want to find voltage across Z2, I know voltage across Z2 is Z2 divided by Z1 plus Z2 times V. It's exactly like as before. The only difference here is that this is a complex number. And this V can be written as some magnitude and some phase. Right? The rest is exactly the same. So this is a voltage divider. If I have a current source, Z1 and Z2, and let's just say I want to find this I know current through this branch is proportional to the value of the impedance in the other branch times the source. So I equals Z1 divided by Z1 plus Z2 times IS. Again, as you can see, it's exactly the same as before. The only difference is that like this is a complex number. And this I is some magnitude and some phase. So we're going to have to deal with complex numbers. The rest remains the same. Right? So let's do a few examples to see how we can actually apply all those methods that we learned before over here. Again, it's nothing new. It's exactly the same as before. The only difference is that we're going to have to deal with the complex numbers. Okay? So example. Let's just say we're given this circuit. 1 ohm. An inductor with value I. A current source with value 2 with phase 0. A voltage source with values 6 and 0. 1 ohms resistance. Another 1 ohms resistance. And a capacitor with value -5. And the question is, what is this I naught? Right? Now let's just assume it's operating at some frequency omega naught. So assuming we have frequency omega naught for both voltage and current source, what is I naught of t? Right? As soon as I find that I naught, I know I naught of t, right? So I'm good. So let's try to solve this problem using different methods, right? Well, let's start by node analysis, right? So method 1, nodal analysis. If I'm doing node analysis, what do I need to have? What is the first step? We need to establish a ground. Let's just say this is my ground. What is the second step? Name the nodes. I claim this is node 1, this is node 2, but I'm not going to name this node and this node. Why? Because remember, as soon as I go to time, from time domain to the frequency domain, which is this circuit, I can treat all the elements as a resistance. If I can do that, then these two elements are in series, so are these two. So I can combine them, right? If I combine them, what is the combination here? There are two resistors back to back in series. The combination would be 1 plus this value, which is minus I. So it's 1 minus I. Right? How about over here? Again, the same thing. They're in series, so I can add them up. So it's 1 plus I. So instead of considering two nodes over here, I can combine them. Right? What I'm claiming is that as soon as I know V2, I know I0. And I don't really have to worry about anything else. I don't have to solve for V1. Right? So let's do the third step. What was the third step? Writing KCL for every single node. So let's just start at node 1. Can I write a KCL for node 1? The same reason as before, we cannot. Why? Because we have a voltage source. And when we're writing KCL, voltage sources are either super easy or problematic. They're problematic if it's between two nodes. What's going on over here? It is between two nodes. So it's a problematic one. What was our solution before? Supernode. We've got to do exactly the same thing. So let's call this my supernode. Now I can write a KCL. Let's assume all the currents are going out. Right? What is this current? That is V1 minus 0 divided by 1 plus I. What is this current? It is V2 minus 0 divided by 1 plus I, 1 minus I. Right? The value of the resistance is 1 minus I. What is this current? V2 minus 0 divided by 1. So that's the current that are going out. It should be the same as the current that's going in. What is the current that's going in? It's 2 with the phase 0. What is 2 with phase 0? What is phase 0 in general? It means it's happening on the x-axis. What does that mean? It means it's real, right? Remember, 2 with phase 0, it is the same as like 2 times e to the power of I0. And I0 is 1, right? So this is 2, right? As soon as I have a supernode, I know I'm losing some information. So I have to utilize the information that supernode has given me. What is the information? Supernode info. Well, I know V1 minus V2 is negative 6 with phase 0, right? Which is the same as negative 6, right? Do you agree I can find V1 in terms of V2 using this equation? V1 is V2 negative 6. You agree with that? Now I can replace this V1 over here and get an equation that's in terms of V2. Remember, the only thing I'm interested in is V2, right? So I can plug it in here. So I have V2 minus 6 divided by 1 plus I plus V2 divided by 1 minus I plus V2 divided by 1. That equals to 2. That is the equation 1, which is this. Right? I have one equation, one unknown. I'm done. How do we do this? I'm going to factor out this V2. So if I do this, I can factor out V2. From first term, I have 1 over 1 plus I. From the second term, I have 1 over 1 minus I. From the third term, I have 1. That equals 2. And I have to take this minus 6 over 1 plus I to the other side. So it's plus 6 over 1 plus I. Right? Right? How do I solve this? Well, I have to find a common denominator and try to like simplify it. So if I find a common denominator, for this one, it is 1 plus I times 1 minus I. If that is the common denominator for the first term, I have 1 minus I. For the second term, I have 1 plus I. For the last one, I have 1 plus I times 1 minus I. This times V2 equals 1 plus I, 2 times 1 plus I, plus 6. Right? What is happening down here? I have Z, which is 1 plus I, times its conjugate. What is it then? I know Z conjugate is x squared plus y squared. So it's 1 squared plus 1 squared. So the whole thing down here is 2. Right? This negative I cancels this positive I. Again, with the same logic, this is 2. So I have 1 plus 1 plus 2 divided by 2. So the whole thing over here is 2. It's 4 divided by 2. How about this one? What is this one? That is 8 plus 2i divided by 1 plus I. Right? What is V2 then? What is V2? Well, V2 is this number divided by 2. Right? So V2 is half times 8 plus 2i divided 1 plus I. Right? So I have 4 plus I divided by 1 plus I. Right? 8 plus 2i, I can factor out 2. Again, I get a division that the denominator is a complex number. How do deal with it? How do we deal with it? Multiply the whole thing by the conjugate of the denominator and divide it by that. So I have times 1 plus I, 1 minus I, divided by 1 minus I. Remember, the conjugate of 1 plus I is 1 minus I. Right? So I get 4 plus I times 1 minus I divided by, again, these are conjugate, so that would be 2. Right? To find the numerator, I have to distribute it. So I'm going to distribute it like this. So I have 4 minus 4i. Then I have to distribute this I. So it's plus I minus I squared divided by 2. What is negative I squared? It's 1. I squared is negative 1. Negative of negative 1 is 1. So this is 5 minus 3i divided by 2. Right? As soon as I know V2, what is I naught? Remember, I naught is V2 divided by 1. So I naught is V2 divided by 1, which is 5 minus 3i divided by 2, or 5 over 2 minus 3 over 2i. Right? Now I have to convert it back in time. Right? What do I need to convert this to time domain? Magnitude and a phase. So magnitude of I naught is square root of 5 over 2 squared plus minus 3 over 2 squared, which is a square root of 34 over 4. Right? I also need the angle, which is the tangent inverse of minus 3/2 divided by pi over 2. What quadrant is this point located in? Fourth quadrant, right? So what it means is that when I'm actually finding that theta, I have to make sure it is in the fourth quadrant. So it turns out this is actually minus 30.96 degrees. So what is IT? IT is the magnitude, which is square root of 34/4, cosine omega naught t, plus phase, which is minus 30.96. Right? As you can see, it's exactly the same as like what we had before. There's nothing new about it. Right? Let's do this using mesh analysis. So method 2, mesh analysis. Again, let me redraw the circuit. This is the circuit. 2 and 0, 6 and 0, 1 ohm, another 1 ohm, and negative I. Right? And the question is, what is the sign of it? Right? If we're doing mesh analysis, what is the first step? To label the loops. So let's call this I1, this I2, this I3. Right? What is the second step? Writing KVL for every single loop. Can I write a KVL for the first loop? Again, just like before, when I'm writing mesh analysis, current sources can be problematic. Right? When are they problematic? When they're shared between two loops, which is the case over here. What was the solution? Super loop. So let's call this my super loop. Now I can write the KVL. So writing KVL for super loop, what do I have? I have 1 times I1 plus I times I1 minus 6 with phase 0 plus 1 ohms times this current. What is the current? What is this current? What is current through this 1 ohm? It is I2 minus I3, right? Because I2 is the same direction as the loop. I3 is the opposite direction. So I have to subtract them. So I have 1 times I2 minus I3. And that should be 0. Remember, the 6 with phase 0 is just 6, right? So I can take that to the other side and simplify it. I have 1 plus I times I1 plus I2 minus I3. That is 6. Right? As soon as I have a super loop, I'm losing information. So I have to utilize the super loop information. What is the super loop information? What is it? It is I2 minus I1, which is 2 and 0, which is exactly 2. Right? So I have I2 minus I1 equals 2. Right? Do you agree I can find I1 from here? Right? I1 is I2 minus 2. Right? I still have like one more KVL to write. I have loop 3. Right? So I have 1 times I3 minus I times I3 plus 1 times, what is the current here? This is I3 minus I2. And that is 0. If I simplify it as 2 minus I times I3 minus I2 equals 0. Right? Again, remember, to find I naught, I need to know I2 and I3. So I don't really have to solve for I1. Right? So let's write everything in terms of like I2. Right? So from this equation, I know I3 is I2 divided by 2 minus I. Right? Let's plug in I1 and I3 in here. So I have 1 plus I1 plus I2 minus I3 equals 6. I'm going to plug in I1. So I have 1 plus I times I2 minus 2. I'm going to leave I2 alone, minus I3, which is I2 divided by 2 minus I. And that must be 6. Right? I can factor out I2. If I do that, I get 1 plus I plus 1 minus 1 over 2 minus I. That equals 6 plus 2 times 1 plus I, which is 8 plus 2I. Right? To deal with this, I'm going to have to find common denominator, which is 2 minus I. So I have 1 plus I times 2 minus I plus 2 minus I minus 1, the whole thing times I2. That must be 8 plus 2I. Right? I need to distribute this over here and distribute I over here. So if I do that, I get I2 times 2 minus I plus 2I minus I squared plus 2 minus I minus 1 divided by 2 minus I. And that equals 8 plus 2I. This negative I squared and this negative 1 cancel. Right? This is negative I, this is negative I, this is negative 2I, and this 2I cancel. So on my numerator, I have 4. And on my denominator, I have 2 minus I. So this is basically 4 divided by 2 minus I. Right? I can find I2. I2 is 8 plus 2I times 2 minus I divided by 4. Right? Again, I can distribute this. And if I do that, I get 18 minus 4I divided by 4. Right? Which is 9 over 2 minus, right? As soon as I know I2, I can find I3, right? Remember, I3 is I2 divided by 2 minus I. So I3 is 1 over 2 minus I times I2, which is 1 over 2 minus I times 9 over 2 minus I. Right? How do we deal with this? I have 2 minus I in the denominator, so I have to like multiply by its conjugate to make sure I get rid of the complex number on the bottom. So I have times 2 plus I divided by 2 plus I. Right? What is 2 minus I times 2 plus I? That's 5, right? So it's 2 to the power 2 plus 1 to the power 2, so it's 5. If I distribute the top, it's 10 plus 5 over 2 times I. Therefore, it is 2 plus half I. Right? I know I2 and I3. What is I naught? It's I2 minus I3. So I naught is I2 minus I3, which is 9/2 minus I minus 2 plus half I, which is 5 over 2 minus 3/2 I, which is exactly the same as what we had. Right? So again, whatever we had still holds true. Right? Let's do this using Thevenin equivalent. Make it a little more interesting. Right? So method 3. Thevenin equivalent. So this is my circuit. Negative, positive, 6, and 0. This is 1. This is another 1. And this is negative 5. Right? And the question is, what is this I naught? Right? How do we do Thevenin? What is the first step in doing Thevenin? We got to determine what the load is. What is the load? This is 1. This one is the load. Why? Because I'm interested in this I naught. So this is the load. Now I know what the load is. I know the rest of the circuit is my black box. Right? What I need to do is to find V Thevenin, which is the same as V open circuit. So step 1. Find V open circuit. How do we find V open circuit? We remove the load, leave it open, we find the voltage across those two terminals. So the circuit would be this one, I, 2 and 0. This is 6 and 0. V open circuit, 1, and this negative. Right? Do you agree V open circuit is voltage across these two elements together? Well, I can combine them. So I'm going to combine this and write it as 1 minus I. I can also combine this as 1 plus I. Right? Again, there are like many different ways of like finding this V open circuit. I'm going to take the hardest route because I want to show you a bunch of things. Do you agree this current source is in parallel with this 1 plus I? As soon as I have a current source in parallel with an impedance or a resistance, I can do source transformation. Right? So I can redraw the circuit as some voltage source followed by some impedance, and the rest of the circuit, sorry, there's nothing over here, right? Right? So 6 and 0. This is still my V open circuit. And this is this 1 minus I. Right? All I have to do is to determine like what these values are. What is the value of the impedance? What is it? Remember, for the source transformation, the value of R did not change, right? So if it's 1 plus I, over here, it remains 1 plus I. Again, we're doing source transformation, right? What is the value of V over here? V equals Ri, right? So I have V, which is I times I, times this R here, 1 plus I, which is 2 plus 2I, right? You with me so far? Is that clear how I got this number and this number? Everybody with me? Yes? Do you agree I have two voltage sources? The polarity for this one is negative positive. The polarity for this one is also negative positive. Do you agree I can combine them? I can combine them into one, right? So I have this 2 plus 2I plus 6, which is this. And then I have 1 plus I. This is the open circuit. And this is 1 minus I. Right? At this point, it's like very easy, right? Because this is 8 plus 2I. I can find voltage across this element, 1 minus I, and that's the open circuit. What is it? What circuit is this? That's a voltage divider. So that's very easy. I'm not going to do that. You can do it. I'm not going to do that. I'm going to apply source transformation one more time, right? So let's apply source transformation one more time. If I apply source transformation, I know if I have a voltage source followed by an impedance in series, I can replace it by a current source followed by an impedance in parallel with it. And the rest of the circuit remain unchanged. What is the value of this impedance? It will remain unchanged. So it's 1 plus I. What is the value of this source? It is V over R, right? So I have my V, which is 8 plus 2I, divided by R, which is 1 plus I. Right? Now I'm going to do the current divider. I'm going to find this I. What is this I? I is 1 plus I divided by 1 plus I plus 1 minus I times my current source, which is 8 plus 2I divided by 1 plus I. Right? This is a current divider. Right? You with me? Yes. No. This is our current source. Right? And the whole thing here is my impedance. Right? So this is, I can treat it as a resistance. If I have a current source in parallel with a resistance, I can replace it by a voltage source with the exact same value of the resistance in series. Right? I just need to compute this value of V, which is Ri. Right? All right. This is easy. This 1 plus I cancels this 1 plus I, right? This I cancels this, right? So all I have is 8 plus 2I divided by 2. So this is 4 plus I, right? If I know current through this, what is voltage across it? Remember, voltage across this is V open circuit, right? What is V open circuit then? It's 4 plus I times current through it. Basically, the current through it times 1 minus I, which is the value of the impedance, right? I can distribute this, and that would be 5 minus 3I, right? What is the second step? I have to find R Thevenin. How do I find R Thevenin? Well, I'm going to look at the black box, which is outside this load, and determine if there is a dependent source in it or not. In this case, there is no dependent source, right? Again, it could have like dependent source, and we're going to treat it just the way that we treated before. Nothing changes, right? But in this case, it's like very easy. So it's basically like the case 1 when we're finding R Thevenin. How do we do this? We're zeroing out the sources and find the equivalent resistance. So the second step is to find R Thevenin. So I have to zero out the sources. What happens to a current source? It becomes open. What happens to my voltage source? It's a short circuit. This is still my load, and I have to find R equivalent or Z equivalent, and the rest of the circuit. Right? This is like fairly easy, right? I have 1 plus I here, 1 minus I over here. So what is my Z equivalent? What is it? It's 1 plus I in parallel with 1 minus I, right? So it's 1 plus I in parallel with 1 minus I, right? Which means I can compute it as 1 plus I times 1 minus I divided by 1 plus I plus 1 minus I, right? Remember, Z1, Z2 is Z1, Z2 divided by Z1 plus Z2. Right? What is the top? It's like one number times its conjugate. It's a real number, so it's x squared plus y squared, so it's 2, divided by I and negative I cancel, so I have 2, so it's 1. Right? What is my Thevenin equivalent? Well, I have my V open circuit, which I already computed it, and I know it's 5 minus 3I. I have my Z Thevenin, which is 1. And now I'm going to have to stick the load back in here, which is another 1. Right? The question is, what is this I naught? Right? Well, I naught is 5 minus 3I divided by 1 plus 1. Right? Which is 5 halves minus 3 halves I, which is exactly as what we had before. Right? Yes. Did you have a question? Oh. Okay. So as you can see, everything remains the same. Nothing really changes. The only thing that changes is that like we're going to have to work with a bunch of the complex numbers. The rest is exactly the same. Whatever method we had before can be applied to the circuit and the frequency domain. What we're going to be doing next lecture, we're going to do one more example, and then we're going to move on to filters. We're going to talk about like filters. We're going to say, now we're looking at the circuit and frequency domain. Let's just look at something that's called transfer function. which is the ratio between output and input. And then we're going to talk about like how we can build like different kinds of like filters. And afterwards, we're going to learn how to draw all these like filters. Any question? All right, I'll see you guys Wednesday.